Bismillahirrahmanirrahim. In this video we will discuss some examples related to the block diagram of a control system. So a block diagram is shown in front of you. This is representing a control system whose input is R of S and output is C of S. We have discussed the rules for the block diagram reduction in the previous video. We can shift the branch left or right, or we can change the position of the summing point, and we discussed how we can do it in the last video. Okay, so now over here if you look at this diagram, what we are going to do, we are going to move this point from here to here. So from this point the signal is going to the G3. The transfer function of this block is G3, and whatever is the input over here, it is multiplied with G3 and is available at this point. So if we move this point to this point A that you can see over here, we have moved it like that. So what we will have to do, the input of this block G3 will be additionally multiplied with G1s. So we will have to remove G1s, so that's why we are going to divide it by G1s. So when G3 input is to be taken from this point, so we are going to divide the gain of this transfer function, the gain of this block, by G1. Okay, so we can move it to this position. Now you can see that these two branches are in parallel. The signal is going over here, and from here it is going to the summing point, and this signal, this is going to the summing point. So these two signals are entering into this summing node. So these two branches are in parallel. So what will be the net combination, net transfer function of this one? When the branches are in parallel, their transfer functions are added up. So that you can see over here, the transfer function of the upper block, that is G3 by G1. So here is the transfer function of one path, and the transfer function of the second path is G2. Okay, so by adding them together we can replace this part with this one. Okay, this part. So one part of the diagram is reduced to one transfer function. And now if we look at this part, here we have the feedback. This is the feed forward path, and this one is the feedback path, right? And the total loop is from here to this one. So this is the negative feedback loop. So we can simplify it using the discussion that we did in the last video, that the transfer function of this part will be equal to the gain of the forward path divided by 1 plus the loop gain, and the loop gain is G1s into H of S, right? So this is the equivalent transfer function of this one. So we can replace this one, this part, with this single transfer function. Now these two will be in series, so we can simply multiply their gains, and that you can see over here, the gain of this part and then the gain of this one. If these two are multiplied, we will get this one. So this is going to represent this control system in terms of the single transfer function, right? So R of S is the input, C of S is the output. So the net gain is G1 into G2 plus G3 divided by 1 plus G1 into H1. Now let's look at this second example that is related to the control system block diagram reduction. A block diagram is given to us and we want to reduce it to a single transfer function. So we can apply all the basic rules for the block diagram reduction. Okay, now first of all, what we are going to do, we are going to move this point, this feedback of the signal, from here to this location. So that you can observe over here, that if we move it back, what will be the impact? At the moment we are taking the input for this block from this point and this is coming through this G4. But if we take the input from here, so G4 will not be present. So we will have to additionally multiply this input with G4, or the transfer function of this block will be updated like this. Here you can see the transfer function is updated to H1 into G4, where G4 is this gain. Okay, and the signal that was going over here, whatever was the signal over here was being fed to this summing node. But when we are moving this branch to this position, we will have to ensure that the signal over here remains same. So it was coming through G4, but we are removing G4 from that path, so we are moving this to this position. So from here now if the signal goes, so there must be G4 on the way, so that the signal over here remains same. It is, if it is BS over here, let's suppose, so it should remain BS. So we are going to add a transfer function having the gain G4 in this path. Okay, so from this system now we have this one, and what we have done this, we have moved this point to this one and we have updated the gain of this path from H1 to H1 into G4, and we have updated the path over here as well, as you can see this G4. Okay, now after doing this one, what we can do, we can move this summing point, we can simplify this path, sorry. So this is the feedback loop, here is the feed forward path, and the signal is being fed back over here through the transfer function H1 into G4. So what will be the net transfer function of this feedback loop? So using the basic rule, the forward path gain is G3 divided by 1 plus the loop gain, and the loop is this one, that is G3 S into H1 into G4. Definitely these are in S to mean H1 and G4. So this is the closed loop transfer function of this portion. This is the feedback loop. For this we have this one. So we are going to replace this one with its gain, G3 divided by 1 plus G3 G4 into H1. So this portion is replaced with that one. Now you can observe that this portion is in series with this one, and if the transfer functions are in series, it's a cascaded system or a series system, then the resultant transfer function of this complete path will be simply the product of these two. So we will be replacing these two with the single transfer function, that is this one. So these two are replaced and shown like that. So over here you can see their gains are multiplied, their transfer functions are multiplied. So G3 into G2 divided by 1 plus G3 G4 into H1. Okay, now what next we can do, here you can observe that we have again the feedback. The signal from here is being fed back through this transfer function H2 to this summing node. Okay, so here is the feedback path. So we can reduce it to a single transfer function, again using the formula, that is forward gain divided by 1 plus loop gain. Okay, so G3 G2 divided by 1 plus G3 G4 H1, this is the forward path in this case, and feedback path has the transfer function H2. So what will be the there in the denominator, 1 plus G3 G2 divided by 1 plus G3 G4 H1 into H2. So this will be the net transfer function of this feedback path. So if we simplify this one, you will get this expression representing the transfer function between this point and this point. So let me call it point A, and this is point B. So between point A and B, this is point A, this is point B, we have now single transfer function that is obtained with the help of this expression. Okay, now if we look at this one, we can further reduce it. Okay, so how we can further reduce it? You can see that these two blocks are now in series. So their net transfer function will be simply the product. So G1 into G3 into G2, that you can observe over here, G3 into G2 over G1 divided by this part. So this is the net transfer function between this point. Let me call this is point A and this is point B. So between point A and point B, we have this single transfer function. Now what we can do, if you observe this one, so there this is basically a feedback path again. This is the feed forward path or the forward path simply, and the loop is over here starting from here up to this point. This will be the loop gain. So now we determine the transfer function. So this is the transfer function of the forward path divided by 1 plus loop gain. So loop gain will be the product of these two, this one and this one. So that you can see G1, G2, G3 into G4 divided by 1 plus G3, G4, H2 plus G3, G2 into H2. So now if we simplify this one, so we will get this expression. Right, so this diagram now can be simply represented with the help of this transfer function, which is obtained after simplification of this feedback loop, right? And now if we replace this one, this is basically the transfer function between point A and point B. Now if we look at this part, the G4 is being multiplied with this one, so G4 is over here. So if now we look at that one, this makes a cascaded system. So we are going to multiply the gain of these two blocks, so we will get this transfer function. So this is the single transfer function relating your input and the output, right? So single transfer function. So we have reduced this block diagram into a single transfer function using the basic rules of block diagram reduction. Okay, now let's look at the next example. Another block diagram is shown in front of you, and we want to determine the single transfer function for this one. So what we can do, okay, so here what we are going to do, you can see that we have moved this position to this one. If we shift it over here, these two blocks will come in series. So how we are going to shift it over here, the output of this one should remain same. So it is getting the signal from here, right? It is going over here. So whatever is the signal coming from here, it is being if we move towards this one, so this will come through this path and it will be additionally multiplied with G3. So what we will have to do, we will have to divide it by G3. So the transfer function of this path will be updated. This will be H1 divided by G3, because G3 will be additionally multiplied over here, because we are now taking this signal from this point instead of taking it from here, right? We are not taking it from here, rather we are taking it from this point. So G3 will be additionally multiplied, so we are going to divide this one by G3. Okay, so now this point is shifted to this one. Now what next we can do, G1 and G2 and G3, they are in series, so we can represent it with the help of this single transfer function, which is the product of G2 and G3. Okay, now if we further observe it, this is going to make a feedback loop, right? So the signal is going to flow like that, and from here there is the feedback coming to this summing node. So we can reduce it by noting down the forward gain. Forward gain is G2 into G3, because this is the forward path, and the loop gain will be from here to here, right? So loop gain is G2 G3 into H2. So this feedback path will be now replaced with this transfer function, the feed forward gain divided by 1 plus loop gain. So that is this transfer function, right? Okay, now if we replace it between this point and this point, so now you can see this G1 will come in series with that one. So simply the gains of these two will be multiplied to get the net gain. So we will be replacing this part with this one, a single transfer function, which is equal to the product of these two. Okay, now what is this new diagram? The signal is going to flow like this, and it is being fed back over here. But now over here is the positive feedback. So it will be this part can be reduced by using the expression of the positive feedback. So feed forward path is this one, right? So G1 G2 G3 divided by 1 plus G2 G3 into H2. This is the feed forward path divided by 1, as it is the positive feedback, so there will be the negative sign minus the loop gain. So what is the loop gain? G1 G2 G3 divided by 1 plus G2 G3 H2, that is this one, multiply by H1 over G3. So this will be the net transfer function between this point A and point B of this loop, okay, and this one, because we have taken the feed forward and the loop gain of this portion. Okay, so if we simplify this one, as you can see over here, the feed forward gain, the loop gain, and then for positive feedback there is the negative sign over here. So after simplifying you will get this expression. So now we can replace this path with this transfer function. Okay, so you will be left with this block diagram now, and in this we have now on the unity feedback, because if there is no gain, it means whatever is the signal over here, the output is being fed back to this summing node. So this makes a negative feedback, so we can use the forward gain, that is this one, divided by 1 plus the loop gain. So loop gain from this point A to point B over here, so that will be the same. So 1 plus this transfer function. So if we simplify, we get this one. So this is the transfer function that is relating our input with the outputs, a single transfer function. So we can reduce any complex transfer function into a single transfer function, and then we can study the behavior of the system by applying different types of inputs. For example, the step input, the impulse input, or the ramp input. We can look at the characteristics and the behavior of the system. Okay, now let's look at another example. So far we have seen that there is one input and the one output of the control system, but there may be the multi-input and the multiple output systems. As you can see over here, there are two inputs R1 and R2, and there are two outputs C1 and C2 of the system, and this is going to explain the relationship between inputs and the output. It's a multi-input multi-output system, so it is basically a MIMO, multiple input multiple output. So as we have already discussed that for an LTI system the superposition holds, that means the net output is basically equal to the sum of the responses of two individual inputs. So in order to determine the net transfer function of this diagram, we will have to consider the inputs one by one. So first of all, we are going to consider that there is only one input R1, right, and the second input is 0. So we are going to assume that R2 is 0. So with that we are going to reduce this diagram. So only R1 is being assumed, that is present. So R1 over here, and then the signal goes to this summing block that you can observe over here, and then from here we are going to look at this one. The signal will have to travel through the transfer function G1, and then we will get the output C1, and from here we have the feedback, right? It is going like this. So now G2, this is the negative feedback and this part is 0, so that negative sign has been taken inside of this one. So this block is now from G2 to minus G2, because we were having it on the negative port of this summing junction. Okay, then this signal will enter into G4, right? Okay, so then onward there is the G4, and from G4 if we relate for the time being R1 with C1 only, so let's track the path of the signal. It goes like that, from here it goes over here, and then from here it goes back. So in this we have R1 and C1. So starting from here, R1 through this summing node, it goes to this block G1. From here it goes to the output C1, and this is the feedback path. It goes through G2, and negative sign over here, that is accommodated over here. Then it goes to G4, right? That is this one, and then from G4 it goes to G3, and finally reaches back to the summing node, that is over here, right? So this is the loop that is relating R1 and C1. So we can simplify this one. How to simplify this one? Here you can see all of these blocks are in series, so their net transfer function will be G3 G4 into G2 with the negative sign, and then it makes a feedback path. In that feedback path, if I see the feed forward gain, so that is equal to G1, and the loop gain is from here till this point, right? So that is equal to G1 G3 G4 G2, and this negative sign is also over there, right? So, and it is the negative feedback, so this is going to be the positive one. Okay, so the net transfer function between input and the output will be given by this expression. Now let's see that how we can relate input R1 with the C2, right? So let me remove this part first of all. Okay, so now we are going to relate R1 with the C2. So starting from R1, first of all we will move to this one summing point, and then we have the G1, and after passing through G1 the signal goes to this transfer function, that is G2. As this is equal to 0, so it will be minus G2, and then the signal is going into G4, and then from G4 we are going to get C2, and from here through the G3 we are going back to the this summing node, right? So we can simplify this one like this. Now what we want the transfer function between these 2 points, C2 by R1, right? So sorry, this is C2 by R1. So what is the forward path? The forward path is this one, G1 G2 and G4, the product of these one with the negative sign because of this negative one over here, and dividing by 1 plus the loop gain. Okay, so what's the loop gain? Loop gain is starting from, let's suppose this is point A, this is point B, so from here to here is the loop gain. So the loop gain is G1 G2 G4 into G3 with the negative sign. Okay, so it is basically minus G1 G2 G3 G4, and it is the negative feedback, so plus and minus will make it minus over here. So this is the net transfer function. So one thing that is to be corrected over here, this is C2 output by input, C2 by R1. Okay, now let's relate the input R2 with the two outputs over here one by one. First of all with C1 and then with C2. Okay, so if I just make it a bit smaller one. Okay, so R2 starting from here, now this is to be considered 0. So the signal goes to the G4, right? We have traversed that one. From here the signal is going into this summing node, and here you can see the negative one, so minus G3, uh, because we are traversing this path, and from here the signal goes to G1, and we reaches to the output C1, and from here we have the feedback path through the G2 back to this one. So here you can see the G2 coming back to this summing point. Okay, now let's develop the net transfer function between this point A and point B. So C1 by R2, that is equal to forward loop gain divided by 1 plus loop gain. So forward gain is equal to this one, G4 minus G3 into G1, that you can see over here, divided by 1 plus loop gain. So the loop gain is minus G1, G2, G3 and G4, right? So this gives you the net transfer function between point C1 and R2, between output and the input. And the last one is to relate this R2 with the output C2. So let's traverse the path. Okay, so first of all, starting from R2, we will have to go through the summing node, right? And then from this transfer function G4 we will reach to the C2, right? So this is the forward path of this one, and then what we will do, we will go through this G3 to this summing node, and this is the negative point of that one, that's why it is minus G3, right? So we are moving over here, then from this point we will enter into the transfer function having the gain G1, and from here we will move towards this path. So this has the gain G2, and then from G2 we will enter over here, this is this summing node, right? So we have this loop. So now how we can simplify, the forward gain is G4 and the loop gain is G4, G3, G1, G2, right? So that is shown over here. So this is the net transfer function between this output C2 and the R2. Right, now let's look at the last example of this video. Here you can see an example. Again you have the multiple inputs. Input 1 have RS, and this is the disturbance DS, and it's a feedback path. Okay, so we want to see what will be the net response of the system. So we will have to apply the superposition theorem. First of all, let's observe the because of RS, and we assume that disturbance is 0. So if disturbance is 0, if this goes to 0, it means this signal plus that one, that will remain same, so that will go to the next block. So we can eliminate this summing node over here, and what we have simply the product of these two, because G1 and G2 will be in series, right? So it is a simple feedback path. So G1, G2 is the forward loop gain, and forward path gain, and the loop gain is starting from here to this point, G1, G2 into H, right? So this will give you the net transfer function when your disturbance is 0. And let's suppose that now the second case, when our R of S is equal to 0, means we are going to consider this one as 0, but we are going to consider the disturbance. So we are developing a transfer function between disturbance and the CFS, that what will be the impact of the disturbance over the output. So we will first of all draw the closed loop diagram for this one. Okay, so starting from this point, this one DFS over here, then we have the summing junction, and if I move in this direction, so this is G2 right over here, so we will reach to the output CFS, and you can see the subscript D over here that I have used to represent that this output is because of the disturbance, and this output was because of the input R of S. Okay, so we reach to the output, and then we have the feedback path. Over the feedback path, first of all we will have to traverse this transfer function, and it is coming into the negative one, but this is considered as 0, so simply it will be considered with the negative sign over here, because 0 minus data, whatever is the signal coming over here, it will be negative of that one. So minus HFS into this G1, and then finally you are entering into the summing node, and that is with the positive sign. So this makes a closed loop path. Okay, so now what is the transfer function of this one? So CDS over DS, so the forward path gain is G2 and the loop gain is G2 G1 into H1. So here is this loop. So this is the loop gain. So this is the net transfer function representing the relationship between this output and the input, that is the disturbance input. Okay, now if you want to find out the net output, you can use the superposition theorem, and the superposition theorem is that the net output CFS is because of the input RFS as well as because of the disturbance. So we have calculated the this transfer function. From here I can say CR of S, that is equal to G1 G2 divided by 1 plus G1 G2H into R of S, right? So we are going to use this one from here. This is the output because of the input RFS, and the second part is the output because of the disturbance input. So now if we add them together, this is the net output of your system, not the transfer function. This is the net output C of S. The transfer function is this one. This is the relating the output with the disturbance, and this is relating the output with the main input R of S. So I hope that you would have understood the block diagram reduction concept. Now you should be able to develop the net transfer function for any complex control system. That's all from this video. Thank you very much.